Hello, IME 146 students. Welcome to our week number 6 virtual lab presentation. Today, we're going to talk all about abrasive manufacturing processes. So far in this class, in IME 145, we talked about the conventional processes, right? Then we talked about the non-traditional processes over the past 2 weeks. So the non-traditional processes were ones that used energy other than shear stress to remove material from that workpiece. Now we're going to go back to the shear stress removal processes. So we're going to go back to abrasive process. We're going to kind of go up on the list here if you're looking at the slides right there. And what we've got to do is we've got to go ahead and talk about all of the abrasive processes that they offer to remove material. Now the abrasive processes are going to still remove material with the shear stress. So really it's only the non-traditional processes that don't use shear stress. But the abrasive processes are kind of in their own subset because they're designed for removing small amounts of material to get you a good dimensional accuracy or surface finish. That's really what they're designed for. But they also work in cases where the workpiece is just too hard or too brittle to process using the traditional processes. So with the traditional processes, we use a cutting tool that has a tooth on it with rake angles, lead angles, and so forth. And that tooth will shear a chip off the workpiece. Well, when we have really hard materials, we got to get a really good surface finish, we don't want to take that large of a chip. We want to take a real small amount of material off that workpiece. And that's what abrasive machining is all about, is removing small amounts of material there. Now you're wondering, what is an abrasive? Well, an abrasive is nothing more than like a piece of sand. So if you've ever been to the beach, you've seen abrasives. So sand would be an example of abrasives. They just have different grain sizes when you go to the beach. It's not all the same grain size. But so all an abrasive grain is a hard crystal either found in nature or manufactured synthetically. So we can have synthetic abrasives or we can have natural abrasives. No matter whether they're synthetic or natural, they all are capable of removing small amounts of material to make small, tiny chips that get removed from that workpiece there. So we use them to lap, hone, buff, and polish workpieces. So if you've ever waxed your car with cleaner wax, then you've used abrasives because the cleaner wax has small abrasive particles in there to remove that clear coat or the oxidized surface on your actual paint of your automobile or the clear coat oxidized surface. Now, I mentioned the abrasives, they could either be natural or synthetic. So for example, like you could actually use walnut shells that after you take the nut out, you have the shell left over. They actually use walnut shells to blast stuff. So they abrasive blast stuff with walnut shells to kind of clean it up. That'd be an example of a natural abrasive. Some other ones that you saw last week, we used garnet, right? So the garnet was a natural abrasive found on the earth. So we just take that garnet and we basically put it through a sieve system. A sieve is a collection of fine mesh screens. So you can get the same exact size abrasive particle out for every single particle right there. So really, they use this to get the natural abrasives. They use sieves in order to go ahead and get it to the right grit size. Because if you remember, they're sized by grit. We'll talk about that again here in a second. Now, so that's the natural abrasives. The synthetic ones are made by man, right? So we have like synthetic diamond. So we have zirconia, silicon carbide, cubic boron, nitride. So there's many different synthetic elements that are going to be very hard particles that we can use to process the kind of the more hardened workpieces. A lot of the natural stuff is used more on the softer workpieces, and the synthetic stuff starts to cut the tool steels and some of the harder metals out there. So no matter whether we have the natural or synthetic though, they have to be carried or introduced to the workpiece somehow, these abrasives. So abrasives are introduced to the workpiece or are basically used in 3 forms. It's how they're actually introduced to that workpiece. So they're either bonded to something. So it's called like a grinding wheel if they're bonded to a wheel or a disc or a ring. Or maybe even just a stick. You could have a bonded to a stick. I have basically a stone, an abrasive stone. That's just a stick that I go ahead and I wipe on the CNC table, or I use to stone the CNC table to make sure it's nice and flat before I put my vices down there. Now, so that's bonded ones. I'm going to show you some examples of all these here coming up. But then there's also coated abrasives. What the coated abrasives do, it's a sandpaper. So if you've ever used sandpaper, that's an example of a coated abrasive. It's actually not sandpaper, it's abrasive paper. So, because sand isn't really what's on there, it's an abrasive. But so you got backings made of paper or cloth in the form of sheets, strips, or belts. So if belt sanders would use a coated abrasive right there. So you got the abrasives on some sort of backing. Now, they can be loose as well. So when they're loose, they're held in some sort of liquid or solid carrier and propelled by centrifugal force there. So it's either air or water pressure or some sort of polymer. We're going to see that when we go talk about extrude hone here a little bit later today. They're actually held in a putty. The abrasive is actually held in a putty. Now in IME 145, we talked about some finishing processes, right? We talked about lapping. We talked about, which is an abrasive process we're going to cover again today. We talked about bead blasting or abrasive blasting, right? Or particle impingement, remember that? So that's an example of a loose abrasive. So we have like or basically bead blasting where the air shoots the workpiece with that abrasive and basically impinges upon that surface and cleans it up. So a lot of that's one example of loose there. So I would know though, for like final exam, bonded, coated, and loose. That's the three ways abrasives come out there in industry for manufacturing. Now, when you have that abrasive either bonded, coated, or loose, it has some sort of grit number. So if you remember, it was 80 grit last week. Sorry, I got bad allergies. Give me a second. So it was 80 grit, that abrasive that we used in the water jet last week during the water jet video where I showed you that. So the smaller the grain size, the larger the number. So it's, if you've ever used like abrasive paper, if you ever did any type of wet sanding, that's like 1,000 and 2,000 grit. So 1,000 is actually rougher than 2,000 grit. 80 grit would be pretty rough, like sandpaper, and then 200, 30 grit. So it's more coarse, the smaller the number there. So what's happening though with that grit or that grain, you think about it, each one of those grits or those grains, like on a piece of abrasive paper, or if it's bonded to a wheel, is going to shear that chip up off the workpiece. So we're still shearing a chip off the workpiece. We just don't have the same rake angle that we would like with a cutting tool, because the abrasive grains are irregularly shaped particles. Now, so those irregularly shaped particles just remove a chip from the workpiece. You also remove some of the particles from the tool or wherever it's bonded to. So you will lose some of your wheel size or your as you use like maybe abrasive paper, it starts to wear down or wear off those abrasives off there. Now, the most popular type of abrasive process in manufacturing is called grinding. So grinding is an abrasive chip removal process that uses a single abrasive grain as the cutting tool. But the thing is, the grinding has a wheel where there's thousands and maybe even almost 1 million grains, right? It depends on the size of the grinding wheel. But the grinding uses a bonded abrasive. So this is an example of a bonded abrasive right here, where you have all the abrasives bonded into this wheel form. You mount this wheel on a spindle and it rotates at some sort of surface speed value. Now, with these grains, these wheels have porosity. Because they're bonded to that wheel, they're porous. So that basically the bond between the different grains has a tad bit of area in between their porosity. That's why wheels or grinding wheels have been designed to grind a certain type of material. So they make ferrous grinding wheels and non-ferrous grinding wheels. So they make wheels that are designed for like aluminum and softer metals, and they make grinding wheels that are designed for steel and harder metals. You would never want to grind aluminum on a steel wheel, because you could have the aluminum melt and get inside of this grain structure and this porosity. Then you have an unbalanced condition on this wheel that's spinning at a high RPM. What happens, it gets so out of balance that it'll basically have a chunk fly out of the wheel and maybe injure the operator. It could cause even death. I mean, so it's a very serious thing not to grind the wrong material on the wrong wheel. So when you go to the hangar, when you get back to when you get back to in person, you're up at the hangar and you see the different grinding wheels up at the hangar. The one that says do not grind aluminum, do not grind aluminum on that wheel. You could cause a serious out of balance condition and cause damage or even severe injury to somebody. So please don't do that. But now these grinding wheels, they get dressed. So I'm going to show you this SME video real quick. It's kind of an older video, but it shows how these grinding wheels work. So here we go. Check this out.
A grinding wheel that has been mishandled can be dangerous.
So yeah, if they have cracks or anything like that, they spin at a very high RPM, you could cause damage to something.
Grinding wheels are extremely fragile and must be handled and stored with care. Wheels should be visually inspected before use.
So these wheels get mounted on an arbor like you see right there. So that's kind of like the tool holder for them.
To assure that a wheel isn't cracked, ring test it using a non-metal object. A good wheel will have a clear ringing sound. A cracked wheel will not. If a wheel has been dropped or appears to be damaged,
do not use it.
Return it to the manufacturer or discard it, but don't use it. Wheel speeds are marked on the wheel or blotter and must not be exceeded. Wheel guards must always be in place before turning on a grinding wheel to avoid injury should the wheel fail. Proper eye protection should always be worn during grinding operations to protect against flying grit.
So this is surface grinding, just so you know, and always wear your eye protection, but we're going to talk about surface grinding next. So check it
and sparks. Proper balance of the grinding wheel is essential to produce high-quality parts. Out-of-balance wheels produce excess vibration, early wheel failure, and...
So right here, I want everybody to see this. This is a burn part. You put too much heat into the part, you extracted a lot of the carbon, and basically you have now created a heat-affected zone on this part. You've destroyed it, basically, by grinding it. So you can actually hurt the part through the manufacturing process if you grind it incorrectly.
Can destroy workpiece surface finish. Grinding wheels may be initially balanced on a balance stand.
It's like, whoops, that was just like balancing your motorcycle tires, or if you've ever done that. So you basically put it on a truing wheel like you see right here.
Stand.
Allow it to balance
Modern
out.
machines are sometimes equipped with an automatic balancing device. With higher wheel speeds, automatic balancing becomes a necessity.
So at the end right there, what they were saying is the CNC grinders actually true the wheel and dress the wheel automatically to square it up. But first, we're going to talk about grinding temperature. When you're grinding, you never make a large depth of cut. What you're going to do if you do a too large of a depth of cut is you're going to put too much temperature into the part, and you saw that marking or the discoloration on the surface. That's a heat affected zone now. So you basically could affect the hardness of your tool, of your workpiece, by grinding too much off. So to reduce temperatures, your depths of cut are usually less than 5 thou. So, and then you can cause residual stresses on that workpiece, distortions, and thermal expansion and contraction. So real small depths of cut right there, just to take a little bit off the surface. That's what grinding is all about. Just getting a nice surface finish and a very tight tolerance. This is how we get tolerance down into the 10,000ths of an inch, 4 decimal places, using these abrasive processes. So in order to get those tight tolerances, the wheel has to have a known form. So you have to know the size of the wheel, and it has to be nice and square and flat, or it has to be at the shape that you're actually grinding. We're going to get into some CNC grinding here in a few minutes and realize the CNC machine will true or grind the wheel to a specific shape. But if you're doing it by hand, you dress the wheel with an industrial diamond. You literally just get on the grinder and you move back and forth with this industrial diamond, and it squares up the face of the wheel. So if you've been to Kevin's welding lab, he never does that. If you look at some of those, because he sharpens his tungstens on them, it makes a big V or groove in the wheel, which is dangerous, actually. I keep telling him that. So you need to always dress your wheel and don't want to ever get a big V or groove in the wheel like I see in the welding labs a lot of the times. You got to go back in there and true those things up, or else you're going to end up having a chunk come out of that wheel. So dressing and truing is something that you normally do. Maybe sometimes they do it in between passes, between roughing and finishing passes. Sometimes they just do it at the beginning of the operation. Sometimes they do it every couple parts. It just depends on how much material you're losing off that wheel. Because remember, the wheel is losing material at the same time that the part is, just not as fast as the part is. Part loses its material a lot faster, but there is some attrition to that actual wheel right there. So that's what truing and dressing is shaping your wheel to the desired shape, your grinding wheel, so then you can use it in the machine to do some grinding. Now, the most common type of grinding process out there is known as surface grinding. So what surface grinding does is it grinds the top surface of your part perfectly flat or very close to perfectly flat, right? So you could almost get perfectly flat surfaces on a part this way. And the parts are usually held in a magnetic chuck. If you look, that's a very large surface grinder right there. So they're usually that when you surface grind something, it's because the workpiece has been hardened and you want to get a tight tolerance on it. So if it's been hardened and heat treated, chances are it's got iron in it. So surface grinders have a magnetic table to hold the workpiece. So they'll actually surface grind the table perfectly flat, put the part on it. You only surface grind it if it gets messed up. But you surface grind the table perfectly flat, you put the part on it and turn the magnet on. The part is now stuck in place and you can surface grind that entire top of the part. Well, if you have a non-magnetic material, you can hold it in a vise in the surface grinder, but most stuff is ferrous here. So this video right here is going to show you an example of some shear blades getting sharpened. So go back to the welding class, but you will take that at some point, MEs. You're going to see here, these are shear blades. The shears cut or shear sheet metal. So those two blades come together at like a 7-degree rake angle and will actually end up shearing or cutting sheet metal. So they're just sharpening those shear blades. They maybe needed to resharpen or they're getting brand new blades. I'm not sure if that's a resharpen or brand new one, but notice they're held on this magnetic table right here. So really the parts are in place thanks to the magnet. So the tooling forces can't move the part because the magnet holds it in place. And it just goes back and forth along the top surface of the part, removing about anywhere, a few thou, no more than 5 thou per pass right there. And the cutting fluid keeps it cool. And the sparks that you see are just the particles or the chips removing themselves off that workpiece. So this is what surface grinding is all about, making nice flat surface on your part. Now, if you needed to make a round part that had a tight tolerance, it would be cylindrical grinding. So in cylindrical grinding, now we have we're grinding hardened steel pins or shafts like you see right there. And you have a rotating grinding wheel now instead of a single point cutting tool like on a lathe. So the workpiece is still turning like on the lathe, but now instead of that single point cutting tool, you have a grinding wheel. And it just comes down and it grinds the diameter of the part right there. So that's how shafts are made that have bearing surfaces that need to ride basically and have a nice tight tolerance and good surface finish. So now, remember that 36-foot long part we saw at the beginning in 145 back with a lathe? Here it is getting roll ground or basically roll ground afterwards. So after they turn it, it's got a helix down the part, right? Because when you do turning, you're creating an inch per revolution value down the part. You can see the surface finish differences right here. So you can see on the right, you have the turn surface finish. Let me go back to that a little bit. So on the right, you have the turn surface finish. On the left, you have the ground surface finish. So to get a really nice surface finish and tight tolerance on this roll, this 36-foot long roll, they cylindrical grind it all the way down. So there's the grinder and it's slowly going down, removing a small amount of material right there. It does this for a while. So we'll move down here and you can see actually how long this cylindrical grinder is. That's a very expensive machine right there. That's over $1 million, that machine. So that's surfaces for flat surfaces, cylindricals for round surfaces, centerless grinding are for pins. So if we had to make like a dowel pin, like we're pressing into our Geneva fixture, so you're going to see we have this Geneva-based fixture. Whoa, this Geneva-based fixture here that you use to inspect your Geneva base, or you will when you get to that lab. And we have hardened steel dowel pins in here that well, you really can't see it, but the hardened steel dowel pins were ground down to a 0.145 diameter. We went from 3/16, 0.1875, down to 0.145. And well, in order to make the 3/16 dowel pin, they had to centerless grind the dowel pin because it's a hardened steel dowel pin. So it gets the entire surface centerless ground. And then I cylindrical ground the top part of it to get it down to a 0.145 diameter. But we're talking about centerless grinding. With centerless grinding, you have one grinding wheel, then you have one regulating wheel, and then you have a work blade right here to keep the part from falling down between the blades. So if you're wondering how they ground carbide tool blanks, in order to get the solid carbide tool, they've got to grind carbide rods. So this one is actually a 330 millimeter rod. This is a carbide centerless grinding station with a gantry loader. So it's got a loader automatically, but they're making these carbide rods right here. So this carbide rod goes into a centerless grinder because the entire rod needs to be one diameter, tight tolerance, and no run out across the shaft. So maybe I don't know what they needed these for exactly. This one's an automated cell, but you're gonna see it puts it into the centerless grinder right here, right? So the robot's moving it in. It basically lets it go back and forth between that centerless grinder. That's how we grind the entire outside diameter. Now, when it's all done, give it a second. When it's all done, we'll come over here. We don't want to watch it grind for 2 minutes. It gets taken out and loaded on the chute. And check this out. Centerless grinding. This is a really good amount of run out. Look at that on the edge of that shaft that long. Whew. So you've learned about run out too. I know you've tested it. I saw a bunch of you in the lab testing it. So that's what centerless grinding is about. So there's 4 types of grinding: surface, cylindrical, centerless, then there's CNC grinding. So this is how all of your taps are made. So if you've wondered, how do they grind, how do they make a tap? It's hardened steel, it's high-speed steel, it's been hardened. How do they cut the flutes into the tap and so forth? Well, they grind it. They CNC grind it. So if you look, here's a hardened worm gear. So this is how they finish off gears after heat treating. So CNC grinding is used heavily. It's how all of our solid carbide milling cutters are made. It's how our tool holders are made. So this first video right here is going to show you a little bit of CNC grinding. So this one is grinding a hob. What a hob is a tool made for cutting gears. It's a gear hob. So they're actually grinding this carbide hob to make a tool. So this is the tool down here on the right, and then they're actually using the grinder to make that tool. So you can see that's how they get all the flutes in there, or the involute curve for the actual. That's how they get the involute curve in there on the hob. Now, there is a place where they dress the wheel. Where is it? I think it was over here. I missed it. Wait. No. They dress the wheel, and that's what I really wanted to show you. That's the relief grinding. One more second. Where did they dress the wheel? Was it way back up here? No, gashing. So what I wanted to show you is they dress the wheel on an industrial diamond here. So they tool change to a different grinding wheel. Let's just stop here real quick and watch this real quick. So they tool change on the grinding machine. This is a very nice grinder, right? CNC grinder. So now that they got the new tool, this is, I guess, for the relief. So it's a different size grinding wheel to go ahead and grind that hob. They're going to, you can kind of see how the wheels formed the actual part. So in order to get the wheel, let's go back to that. In order to get this wheel with this exact form, they grind it on an industrial diamond. And I know my next video shows that. So let's watch this one. This one's got a good music, so we'll turn it up, right? So give it 1 second here. So what they're going to do here is they're making tool holders for a Haas CNC machine. So all those tool holders on our Haas CNC machines have basically hardened steel tool holders, right? In order to locate in that space. What this company's doing is grinding those Haas Cat 40 tool holders. So if you look here, it's the best video quality, but so we're gonna go right here. So this is that tool holder, right? So it's a hardened piece of steel. To get that 40 taper, they have to go ahead and grind that surface right there. So the probe's coming and touching, finding where the part is. See, that's the probe. The probe gets put away. It knows where the part is now. It's going to come down and grinding. But here's what I really wanted to show you, the dressing of the wheel. So this is an industrial diamond. Let's turn off this music. This is an industrial diamond, and it squares this wheel so it knows the exact shape of that wheel there. Then they go to grind the outside diameter of that tool holder right there. So they're making tool holders with this grinder. They're hardened steel. They're hardened tool steel. You can't cut them any other way. You got to grind them. So that's what grinding is all about. Now, they do have abrasive belt grinding. Now, this time we have basically coated abrasives, right? So abrasive belt grinding is usually done manually. It's not the most accurate process unless you got a robot involved. You'll see down there on the bottom left corner, there's a robot deburring those propeller castings. So that might make it a little bit more precise. But again, when you have a belt sander, it just kind of clean up metal surfaces on castings. There's grinding wheels. You can remove some stock and you just kind of deburr. Sometimes we have abrasive belts to deburr steel workpieces after we cut them off the saw. It just depends. So there is abrasive belt grinding. I'm not going to ask you about that though. I was going to ask you more about surface grinding and the other grinding processes. There's also abrasive cutting. So if you've taken Kevin's welding lab, you've used the abrasive chop saw. If you have a little Dremel tool and you've ever used the cutoff wheel on a Dremel tool, that's an abrasive cutoff wheel. And so all they are just abrasives mounted to a disc. And the traditional metal saw continues to be more economical for large sections of certain materials. But sometimes when you have like steel pipe and tubing and you just got to cut it to weld, this is going to be a faster way to go ahead and cut stuff if you're not worried about the edge surface quality. Because here you're melting the material and you're creating large burrs, and it just really depends on if abrasive cuttings, depends on what the end use of the product is. If abrasive cutting will work well for your process. We don't really use them in the machine shop. Those abrasive sparks that you see will get all in the ways of those Haas machines you see behind me and destroy them. So we keep the abrasive stuff in Kevin's lab unless it's a water jet or a belt sander. So we can kind of clean up the belt sander corner and not get abrasives everywhere. So that's what abrasive cutting is all about. I'm not going to ask you about that ever again either. I am going to ask you about honing though. What honing is we're finishing the internal bore of an object. So honing's for round internal bores. So you have a rotating tool with honing carrying abrasives. So this is the actual tool over here on the right. So the tool has abrasive stones on it. You can also, if you've ever heard of honing a knife, it's because you have a honing stone. It's like the same type of stone that's on this tool. And you rub your knife against the stone at a certain angle to get that sharp edge. So that would be an example of honing a knife. But honing in manufacturing is finishing the internal bore of something. It's used heavily on cylinder bores for hydraulic systems. It's used heavily in automobile engines too. Every piston bore is honed before they go ahead and put the pistons and the rings in a cylinder there. So it's how you finish the internal walls of a cylinder. Now it's generating good cylindricity when you do honing. So GD&T, geometric dimensioning and tolerancing, we have cylindricity, getting a really good, perfect cylinder. So when you have like a hydraulic cylinder that's moving back and forth and has to keep pressure in there, you want good cylindricity. When you have an automobile piston, a cylinder which the piston's traveling in, you want good cylindricity. You don't want it to go ahead and get less and more compression as it goes up and down because you don't have a perfect cylinder there. So you hone cylinder bores a lot of the times, or interior tubes. So what you have is you have expanding abrasive stones that abrade against the workpiece's surface. Now those stones, once they abrade against that surface, they're going to remove small amounts of material, making you have a good form and a nice cross-hatch pattern in the surface. So it's leaving you a good surface finish as well. So this video right here is going to show some honing. So what they're honing here, let me go ahead and open this up first. They're honing some gears. So what we have, I'm not going to go ahead and turn on the sound, but this is the hone. So you'll see that the gray part on the tool is the stone. The yellow piece is kind of like a flute for the chips to kind of relieve themselves out of there. Now, these gears are going to go on a tight tolerance shaft, and you're going to want to hopefully get maybe 100,000 miles out of your transmission, right? These are transmission gears. So if you don't have a tight tolerance and good surface finish on that internal hardened gear surface that's riding on that shaft, it's going to gall itself over time. So you want hardened surfaces that have smooth and tight tolerances to ride over each other in a nice oil bath. That's what a transmission gear is all about. So they use this honing process to hone those internal bores. Now over here, they have rocker arms. So if you're an engine person, you know what a rocker arm is. It moves up and down, it rocks back and forth. So the cam pushes it, it rocks. like this and pushes down on a valve stem to open up the valves of an engine. So here, we're honing rocker arms. So this fixture, it's a pretty ingenious fixture. They put it down on this fixture. It locates the part in space, and then they line bore these rocker arms together. If you look at them, they're not line boring. They're honing the rocker arms together. So basically they go through and the hone will come down and basically hone that surface to a tight tolerance right there. So it goes through, you have the link, you can see some of those other parts that they're actually honing. There's some more rocker arms that they're actually honing there. So a lot of your automotive parts and aerospace parts are honed. If you're gonna have that gear, if that hardened gear is gonna ride on a shaft somehow, you gotta have a good surface finish and good tolerance for that internal hole in there. You gotta hone them. Here's a very large hole getting honed. Just wanted to show you, this is a hone too. So you're just trying to get good final dimension size and tight tolerance. Now I mentioned that all engines are honed as well. Well, an engine is cast, right? So you get the engine block cast. Once the engine block's cast, you need to go ahead and size the bore somehow. So what you do is you do boring. You enlarge the bore with a single point cutting tool. Well, what that leaves is it leaves a helical shape or path down the cylinder of your engine. So what you have to do is get rid of that helix, because if you have a helical path or surface down your cylinder, you're not going to conceal for compression. You're going to have spiral leakage down that tool path. So what they do is they get rid of that tool path by honing that last little bit amount of material out of the cylinder, either using a ball hone, like for example, if you've ever done it in your garage, or they have specialty hones for the actual cylinders in the factory. But you'll see what it does is it leaves this crosshatch pattern, which is actually a good surface finish pattern. It looks like it's roughed up. It actually isn't. It's better surface finish than the board pattern. And that crosshatch will allow oil to kind of stick in that crosshatching and kind of assist with compression between the rings and the piston. So that's just one example right there. I know some of you IMEs are probably really interested in the engines, and this is kind of cool for you. So this honing, ball hone, that's how we basically smooth out the cylinder of our engine before we put the pistons in it when we're manufacturing engines. Now, so that's honing. Honing finishes internal cylinders to get good cylindricity and good surface finish pattern. Now, abrasive flow machining is a little bit different. Here, we now have the media suspended in it's in a putty. It's like a fluid. So the abrasive particles, the carbide abrasive particles are in a putty. Think of it by like having abrasives in Play-Doh or putting sand in Play-Doh and forcing it through a hole. That's what this is. Sand and Play-Doh forced through a hole. Just a little bit more technical than that. So what we've got these abrasive particles in the media. They basically contact the internal surfaces of the part. And you have basically a hydraulic ram forcing it through the actual ports of the part right there. So now this is done for internal passageways. So if you have to smooth out internal passageways so they flow better, you can go ahead and use this abrasive flow machining. It's used heavily in the aerospace industry to go ahead and deburr castings. So when you have a casting, you don't want any flash or anything like that if you have some sort of port that's going to carry a fluid. So the deburr internal casting ports with this abrasive flow machining process. Now what I have videos from the aftermarket automotive industry. The bottom one here, I'm not going to watch during this time, but they're abrasive flow machining some Ferrari heads and Lamborghini heads, and they're getting more power out of them because they're able to smooth out where the air flows into the engine. But I've got diesel exhaust manifolds instead. It's a better video because it's HD and it just comes across a little bit better. So we're going to watch this process. It's called extrude hone. So Extrude Hone is the company who invented it. It's patented and it's owned by Kennametal. And so that's why you call it Extrude Hone technology, but it's abrasive flow machining is what it's classified as. Here we go.
Hey everyone, Lance Brown here with Performance Diesel Inc., PDI. We're here in Irwin, Pennsylvania at Extrude Hone. Today we're going to walk you through one of the finishing processes that goes into our exhaust manifolds. The process that we will show you here today is abrasive flow machining. Very neat process, allows us to finish the insides of our exhaust manifolds, which provides the smoothest, most efficient airflow possible. All right, as you can see behind me here, this is the technique called abrasive flow machining. They're pumping media material through the internal portion.
They reuse that media, by the way. It goes back down into the floor where the piston is, and they push it through.
Of the manifold, smoothing out all of the porosity. It's being forced through the manifold. The machine behind us is actually underground about 12 feet where it holds the media material, and the large hydraulic cylinder forces the material through the plumbing and flows through the insides of the exhaust manifolds. The media is a putty-like substance with silicon carbide. The silicon carbide is what gives it the abrasive. As it flows through the insides of the manifolds, it is smoothing out all porosity and giving them the absolute best smooth finish.
If you think about it, it's flowing the same path that air would want to flow too. So it's basically smoothing out the transition, or where all the sharp transitions that are inside that casting, and it's going to make the air want to flow a lot better, giving you more power, it's giving you less frictional losses on the walls of that part, allowing more air to flow through the motor, allowing you to burn more fuel and air and make more power, right? So there we go. It's a lot of pressure to make it go through that manifold like that.
The end result from the AFM. You have a smoother interior surface on the manifold, reducing any wall drag, which retains heat and causes warping and cracking in your exhaust manifold. This is what helps us produce manifolds with an industry-leading 3-year manufacturer warranty. Another part of the quality control here that comes from...
So now they put it, well, we'll watch this
actually.
actually.
Well, all of our finished product is monitored and measured to precise measurements. All right, everyone, I hope you enjoyed.
There we go. So that's called abrasive flow machining. So if you want to see it done on exotic car intake manifolds, it's this next video down here. You have the link. Now, the last one we're going to talk, well, the abrasive manufacturing process that gives us the best surface finish and the tightest tolerances ever possible is called lapping. So lapping now will produce an accurate, smooth, matte surface on your part. It could even be a polished surface depending on the type of lap compound used. So I can finish flat, cylindrical, or curved surfaces using lapping. There's different processes for curved surfaces versus flat, or different type of tool and how you lap it. But other than that, the process is the same in terms of how it works. So now with lapping, we have abrasive particles mixed in a slurry. Remember, we talked about abrasive slurry with ultrasonic machining last week. So we take that abrasive slurry, it has a certain grit size in that slurry, and we then have basically, we have a liquid cutting tool. The cutting tool is the abrasive in that liquid. And we put the slurry on a motorized platform called a lap plate. So it's a lot like a record player. It goes around in a circle, and you basically have a felt disc on top of that circle that's going around, and you put the part down on it. So there's hand lapping and automatic lapping. There's 2 ways to do it. Hand lapping, you might do this in a material science class here at Cal Poly. You lap your material samples in order to polish them. Then you basically etch them with acid and look at the grain structure. So the reason we lap our material science samples is we want a really flat surface, because if we're going to put it on a microscope to look at it, that flat surface must be perfectly flat on the microscope stage. So we lap material science samples, we etch them with acid to get rid of that top surface, because when you lap them, you rub the grains or the crystal boundaries, the grain structures on top of each other, and you can't actually see the boundaries. That's why you have to etch it with acid to remove that top surface, and then you can look at the part. But that's material science. We're talking about lapping here. So what really lapping gets you the most extreme dimensional accuracy out there. So if you look, we can get the best surface roughness with this lapping. That's how they make our surface plates. So if you've wondered how they make that surface plate perfectly flat, almost perfectly flat across that large plate, they sit there and lap it with a cast iron plate. Then they have a laser interferometer to go ahead and see how perfect they are. When they see a high spot, they got to keep lapping that high spot down till it basically comes perfectly flat there. So this first video here is showing you automatic lapping. So what this one's going to do, we have the parts here on the right down there, and they're throwing the slurry on this giant spinning record player. Now the parts are moving around in an orbital motion, and they're basically polishing them themselves on that slurry and that felt disc right there. So that does this for 1 minute and 26 seconds, but that's a lapping machine. Doesn't look very clean, huh? Because you got that slurry on it all day long. So that's one type of lapping. Now, this lapping process right here, glass. So I mentioned it, you could do it on curved surfaces as well, right? So now they're plano poly, they're lapping a glass lens. So after you maybe cut it to the right shape using your ultrasonic machining non-traditional process, you might want to lap it to go ahead and get it basically polished or nice and clear. So they said we got some nice, but whoops, let me just press play here. Blurry here, and then you have the felt disc rubbing itself on top of that glass surface, polishing it. If you've ever had to repolish your car headlights because they got foggy, it's almost like doing that. You're using an abrasive grit to kind of just take off that top polished surface and polish back those headlights shiny again. So hand lapping now is usually performed on what we call a lapping plate. You have a cast iron plate with grooves in it. So you put the compound on it and you actually lap the steel parts directly on the cast iron plate. So harder steel parts get lapped on these cast iron plates, and it just takes off of any of the peaks and valleys on the part and makes it really smooth right there. So that's what lapping's all about. Now here's some examples of them lapping a surface plate. So in order to get that surface plate, you'll see he has a laser interferometer here. So he's able to tell very slight deviations in the flatness of this surface right here. Once he figures out where that deviation is or that high spot, they get the cast iron lapping plate out with some lapping compound, and they basically rub it until that high spot comes down and you no longer have that high spot. Because if you think about it, what's sticking up is the high spot that you're rubbing. So you just keep rubbing that high spot until it goes down and nice and flat again right there. So that's how your surface plates are manufactured. I found some pictures of them reconditioning surface plates. So when your surface plate needs to get calibrated, someone actually comes into the shop because of how heavy they are. So you have the person come into the shop, they measure the surface plate, they again basically relap it, they remeasure it, it gets a first article inspection on that surface plate. Now it's qualified to be able to measure in the aerospace industry or the automotive industry. So you've got to get your stuff calibrated. You've got to have a calibration record if you expect to be an ISO 9000 certified shop out there. So that actually right there, that's lecture 6 of IME 146. And we have now covered all of the machining processes we're going to cover from 145 and 146. In the next 2 weeks of class, we've got 7 and 8 before 9's going to be just basically a final exam review, week 9 lecture for me, or weekly lab presentation. Week 9 will be final exam review. Week 7 and week 8 are going to be air motor project. Because you didn't get to go do the air motor project in the lab, we're going to do it somewhat virtually. I'm going to talk about production manufacturing with you and how it's a little bit different than the way we've manufactured everything with one-off at this point. So everything you've made has been just a one-off. We haven't built stuff in batches and basically cells. So we're going to set up this lab in a cellular manufacturing format and manufacture the 6 air motor parts and do a little bit of design analysis on them as well. We're going to do some allowance clearance calculations on the air motor assembly. We're going to figure out how they're made. I've got videos going through making all 6 parts. We're going to talk about why we do things differently in some of the operations compared to what we would have done if we were just making one-off parts. That's going to get you kind of some experience on how batch manufacturing is done, how we produce parts in batches. And that way kind of shows you why we need to have all of these tolerances and interchangeability by this batch production. But I'd like to kind of leave you with this graph right here, this graph right here. It's surface finish versus machining process. Hopefully you now know that the tighter the tolerance that you specify on your engineering drawings, the better the surface finish is going to be, because the manufacturing process that has to produce tight tolerance features gets good surface finish. Because really, the surface finish and the tolerance is really hand in hand, right? Because the surface finish is the peaks and valleys on your part. If you have a real rough surface finish, you're not going to be able to have a tight tolerance because you've got a lot of differences between those peaks and valleys. So when I start to look at the roughness average here. That's how you measure surface finish, RA. We talked about that in 145, right, with the screwdriver. But if we're in Kevin's class and we're flame cutting stuff, you probably have done that if you've been to his class, you get horrible surface finish if you remember that, right? So if we look at that, our roughness average is not doing so well there in micro inches, right? But when we come back over here, so when we come back over here, we get a 32 surface finish is about what you get in milling. So you can get a 32 in milling if you look. You can't really get any better than 32. It's pretty hard to do that. So we're getting better as we go this way, right? So we learned about milling, we learned about broaching and reaming. So if you look, reaming can do a little bit better than milling, right? Then we got laser cutting, we talked about that. Electrochemical machining gets you really good surface finish, right? Boring, turning, electrolytic grinding is a non-traditional process. It's called EDM grinding. So they do EDM grinding. I didn't cover that. That will get you a really good surface finish. We've got roller burnishing, which we talked about. That was a finishing process. We talked about burnishing, remember? Grinding, honing. Another one we didn't talk about was electropolishing. Oh yeah, we did talk about electropolishing in 145. So we talked about that. We talked about regular polishing, lapping. And then the only thing, super finishing, would give you the best surface finish, but that's a non-traditional process where they flash temperature at it right away, really quickly, high impulses. And it basically burns off the peaks and valleys instantaneously as it flashes high energy at it. It's a very interesting process. Check it out if you're interested. But for the super finishing, but lapping, again, if I ask you on a final exam, what's the material removal process that gives us the best surface finish and the tightest tolerances, it's gonna be lapping. Then we have all of our casting processes out here and how we get our raw materials. Sand casting, rolling, forging. So these are all the ways we get our raw material. You're going to see our raw material does not have anywhere close to the surface finish that we could actually get with our machining processes. So I know you've learned a lot about machining. We're going to continue to do it over the next 3 weeks before we take that final exam in week 10. But I hope you had a great week learning about abrasive processes. Remember, the workpiece is too hard. We got to cut it with an abrasive. If it's got a really fine surface finish call out, or if it's got a tight tolerance requirement, it's got to go to an abrasive process. We conventionally machine it first, and then we go ahead and use the abrasive processes to get us down to that tight tolerance. Or we conventionally machine it to the right size. We heat treat it, and then after heat treatment, we use an abrasive process on it to remove a small amount of material to get it back into the correct size, because heat treating will cause it to twist and change to all different sizes. So that's it for this week. Have a great week, everybody. Enjoy your week 6. You're on to laser cutting this week in your face-to-face labs this week and next. So enjoy your laser cutting lab and checking out the profile tolerance on the MicroView CMM. So you're gonna inspect a part on the MicroView CMM. It's gonna inspect, I think, like 70 something features in like a minute and a half. So you're gonna see how technology has allowed us to inspect a lot quicker than using the traditional methods. See ya. Have a great day.